Hi guys, this is Abhi from Engineering Master. Welcome to the another episode of Engineering Master. In this video, we are discussing about high voltage cables. High voltage cables also called as high tension cables. We will see high voltage cables and its applications, what is the reason behind the smaller dia of the high voltage cables, cable calculations and practical problems. What is high voltage cable? High voltage cables or high tension cables, it's a cable used for the transmission of electricity in high voltages. The cables used in high voltage transmission are called HV cables or HT cables. If you look at the high voltage cables, you can see it is smaller in dia compared to the low voltage cables. If you observe a distribution transformer or step down transformer, you can see the dia of incoming cable size is smaller than the dia of outgoing cable size. The conductor size or cable size is decided by the current carrying capacity of the cable. In high voltage transmission, the voltage will be high, the current will be low. In LV side, the voltage will be low, the current will be more. If the current is more, we need bigger cables. If the current is less, we need smaller cables. That is the reason behind the smaller dia of the HT cable compared to the LV cable. This is a part of a single line diagram from one of my earlier projects. You can see the high voltage cable is coming to the project and it is going to the HT panels. From HT panels, the cables are going to the transformer incomer. Outgoing of the transformer is connected to LV panels and it is coupled through a bus coupler. From LV panel, different cables are going to the load. This is the single line diagram. If you observe this single line diagram, you can see the size of the incoming cable, HV cable, is 3-core 240 square mm aluminum cable. The incomer of the HT panel is same. But if you look at the outgoing, you can see the same cable there. 3-core 240 square mm XLPE aluminum armored cable. In LV distribution boards or LV panels, the size of the incoming cable will be more than the size of the outgoing cable. In this HT panel, the size will be same for the incoming and outgoing cables. What is the reason behind this? Keep watching this video, you will get a complete understanding about this. From the HT panel, cable is going to the transformer incomer. You can see transformer outgoing is connected to the LV panel. If you look at the LV panel outgoing, you can see 4 numbers, 3.5 cores, 300 square mm cable is there. What is the size of our incoming cables? It is 1 run, 3 core, 240 square mm. Our one of the outgoing is 4 run, 3.5 score, 300 square mm. Why it is like that? The reason behind is, in LV side, the line voltage is 415 volt. In HV side or HT side, the line voltage is 11 kV or 11,000 volt. If we increase the voltage, the current will reduce. The conductor size is decided by the current carrying capacity of the cable. If the current flowing through is less, then cable size will be less. We know HV cables are used in high voltage transmissions. Why is electricity transported in high voltages? There are some advantages of high voltage transmission. It will reduce the power loss. It will reduce the cost of power transmission because the conductor size will be less. It will improve the overall efficiency of power transmission. Due to this reason, electricity is transmitted at high voltages. So let's look at a problem. Let's calculate current. A 200 kilowatt 3-phase AC power transmitted 1000 volts and 10,000 volts. Assume 1 ohm resistance in cable. So we have to find the current in both the scenarios. In scenario 1, the equation for power equal to P equal to root 3 VI cos phi. From that I, the current equal to power divided by root 3 into voltage. If we are substituting this value, the power is 200 kilowatt, 200 into 1000. If we are converting this into watts. Divided by root 3, 1.73 into voltage. The voltage in first scenario is 1000 volts. If we are solving this equation, we will get 115.6 amps. If we are transmitting the power of 200 kilowatt in 1000 volt, the current will be 115.6 amps. In scenario 2, the transmission voltage is 10,000 volt. The equation will remain same. I equal to P divided by root 3 into V. So our power is same. 200 into 1000 divided by, what is our transmission voltage? Transmission voltage is 10,000 volt divided by 10,000 into 1.73 root 3. The answer will be 11.56. From these examples, you can see if the voltage increased from 1000 to 10,000 volts, the current decreased from 115.6 amps to 11.56 amps. In first scenario, we need to transfer current of 115.6 amps. So the cable selection will be based on this current. In second scenario, we need to transfer only the current of 11.56 amps. So the cable sizing will be less. In most of the countries, electricity is generated at 11 kV or 11,000 volts. It is stepped up to 220 kV for long distance transmission. In India, maximum transmission voltage is 765 kV. HV cables can be divided into two types. The first one is earthed cable, second one is unearthed cable. Before entering into the topic, we need to know what is earthed and unearthed systems. We know the transformer windings can be connected in star or delta. In star connection, the common point is called neutral. The neutral is connected to the ground or neutral is earthen through the solid wire. If the neutral is earthed through a solid wire, in this system is called earth system. In that scenario, what happens? For example, in 11 kV system, in that scenario, the line to line voltage will be 11 kV. What is the voltage between phase and neutral? The phase and neutral voltage will be 11 kV divided by root 3, 1.73 kV. This type of system is called earth system. In higher capacity transformers, this direct earthing may cause the problems to the winding due to the back current. We will earth the neutral through a high resistor. So in this scenario, what is happening? The line to line voltage will be same, 11 kV. The phase to neutral voltage tends to be the same. So in that scenario, line to line voltage will be same, phase to neutral voltage will be same, 11 kV. So this type of systems called unearthed systems. In delta connection also, there will be no neutral, right? Line to line voltage will be 11 kV. Keeping in mind, if you go to earth cables, what is earth cable? In earth cable, for example, in earth 11 kV cables, insulation between the lines, for example, R and B phase, it will be according to the 11 kV. That is, it will withstand 11 kV voltage. But insulation between line and ground, so outer insulation and the cable insulation will be based on the 11 kV divided by 1.73. So that is based on the phase voltage. The phase voltage equal to line voltage divided by root 3. So basically, the insulation between the phases will be thicker. The insulation between phase and outer covering will be thinner. This type of cable called earth cable. In unearthed 11 kV cables, the insulation between the line, that is R and B phase, will be based on the 11 kV voltage. And insulation between one phase and outer covering will be also based on 11 kV voltage. Unearthed cable has thicker and more effective insulation between the phase and the outer covering. That is the difference between earthed and unearthed cables. Let's learn high voltage cable sizing. There are 4 steps for high voltage cable sizing. First step is calculate minimum cable size based on short circuit levels. Second step, cross check the cable size with load and correction factor. Third one, cross check the short circuit rating of the cable. Fourth one, cross check the voltage drop of the cable. Let's go into details. The first step is find the minimum cable size of the cable based on the short circuit levels. The equation for HT cable size is, for the copper cable, equation is ISH into root T divided by 0.143. For the aluminum cable, the equation is cable size equal to ISH into root T divided by 0.094. In this, T is the fault withstand time for HT circuit breakers. ISH is the short circuit current of HT systems. We have to find ISH. T normally we will take as 0.5 to 1 second. 0.143 is the cable factor for copper. 0.094 is the cable factor for aluminum. So only one element missing is ISH, short circuit current. How to find ISH for HT system? The step 1 is identify fault MVA. What is fault MVA? This is the apparent power during the fault condition, typically given in MVA. Second step is determine the system voltage. What is the voltage level of the system? Is it 11 kV or 33 kV, 110 kV, etc. We need to determine the system voltage or line voltage. Third one is apply the formula. Substitute the values in a formula. The formula is short circuit current IS equal to S fault MVA divided by root 3 into system voltage or line voltage. In this equation, S fault equal to fault MVA, V line equal to line voltage. We know electricity is transmitted through a grid, right? In this grid, a small portion is our project. We have a transformer for our project. So if you look at the grid, you can see 11 kV voltage distributed in so many ways. It has projects, it has normal distribution transformers, and it is applied to villas, etc. Fault MVA calculation for this grid is very complex procedure. In building construction project, as a building designer, it is almost impossible to calculate the fault MVA of the grid by an MEP designer. But we need data, right? We need fault MVA. Where we will get this? This fault MVA levels is given by the power supply providers. You can approach your power supply provider in your area. They will give you the design consideration for fault MVA for your project. This is an excerpt from the design guidelines of ADDC, Abu Dhabi Distribution Company. You can see the short circuit levels are directly given there. You don't need to calculate fault MVA. The short circuit levels are directly provided. Just substitute this value in the cable sizing equation. You can find the cable sizes. So if you look at another example, this is an excerpt from SP Energy Networks Scotland. You can see the fault MVA and kiloampere ratings or short circuit current are given as a table. You can see 33 kV substation in Scotland. Fault MVA is 1000 MVA. Then short circuit current is 17.5 kiloampere. So almost all the places in the world, you will get this data from the power supply company. In some areas, the power supply company will not provide you the short circuit current. They will give you fault MVA levels. After finding the minimum cross-sectional area based on the short circuit levels, the next step is cross-check the cable size based on the load. The logic for this is cable current carrying capacity should be always greater than load current divided by correction factor. We have discussed about this in detail in our LV cable sizing video. I will provide the link in description box. From where we will get the load current? We will get the load current from the equation P equal to root 3 VI cos phi. So I have prepared an Excel sheet for you for the easiness of the calculation. I will provide the link in description box. Please download that. In that, just enter the voltage and the load. You will get the load current. The next thing is correction factor. Where we will get the correction factor? We will get the correction factor from the cable catalog. Almost all the cases, high voltage cables are laid in underground or buried. For overhead transmission lines are used. So we have to find the derating factor in underground situation. There are 4 derating factors for the cables which laid in underground. First one is derating factor for variation in ground temperature F1, derating factor for depth of laying F2, derating factor considering the thermal resistivity of soil F3. If the cable laid directly in the ground, derating factor for touching F4. Overall derating factor equal to F1 into F2 into F3 into F4. All this derating factor, you will get it from the standards like BS 7671 or from the cable catalogs. Cable catalog is the cheapest way to get these values. I will provide the link of a Havells cable catalog in the description. You can download it from there. After doing this exercise, you have to check the short circuit current and the voltage drop of the cable. Let's solve a problem. Fault MVA for 11 kV line in the state of Telangana in India is 350 MVA. Find the short circuit current and cable size. This is a practical scenario. If you are a designer, you will face this scenario. So, S fault, the fault MVA equal to 350 MVA. V line voltage equal to 11 kV. What is the equation? Short circuit current equal to S fault MVA divided by root 3 into line voltage. If you are substituting values in this equation, the fault MVA equal to 350. We are converting into kVA. 350 into 1000 divided by, what is the root 3? Root 3 is 1.732 into 11. What is the value of this? The value of this is 1837077 ampere. We can say 18.37 kiloampere. So we got ISC, short circuit current, as 18.37 kiloampere. What are our equation for cable sizing? For copper, equation is ISH, short circuit current, into root T divided by 0.143. For aluminium, ISH into root T divided by 0.094. T I am taking as 1 second. In India, for higher size cable, aluminium is the preferred material. So I am substituting these values in the aluminium cable size equation. The cable size equal to 18.37, that is ISH, into root T. Root T is root 1 divided by 0.094. The answer is 195.5. No manufacturer is making the cable in 195.5 square mm. So we are selecting the next available size. Next available size is 240 square mm. So our cable selection is 240 square mm. Aluminium 11 kV unearthed cable. I am preferring unearthed cable because it has more insulation. Let's look at the current carrying capacity of our selected cable. This is the Havells cable catalog. In that you can see 11 kV section, 11 kV by 11 kV. Our cable is unearthed grade. So this is the sheet for unearthed 11 kV cable. In that we have to find our cable size. Our cable size is 240 square mm, right? For the 240 square mm, current carry capacity on the ground is 315 ampere. So our cable current capacity is 315 ampere. Then we have to cross check it with the load current. So what is the logic? Cable current carrying capacity always greater than load current divided by correction factor. Assume our load is 1000 kilowatt or 1 megawatt. What will be the load current? Just enter the values in our Excel sheet. Voltage equal to 11,000 volts. Load equal to 1000 kilowatt. So what is our current? The load current is 65.69. Then we have to find the correction factor. Let's go back to the cable catalog. In Havells cable catalog, you can find basic assumptions for current rating and rating factors. The depth of laying is given there. up to 11 kV 900 mm, more than 11 kV 1050 mm. But I am considering my cable laid in 1050 mm only. So 1.05 meter is our depth of the cable. So our depth of laying is 1.05 meter. The first rating factor related to variation in ground temperature. This you have to select the actual value in your area. I am assuming my ground temperature is 30 degree. Then my value for the XLP insulation is 1. So F1 equal to 1. Then we have to find F2. F2 is rating factor related to variation in ground thermal resistivity of soil. So I am assuming my thermal resistivity of the soil is 150. So my rating factor is 1. This also you have to select your actual value. Where you will get the ground thermal resistivity, you have to conduct some test. Or you can ask your civil team. They may have done the soil test. In that, it may be specified. If it is not specified, then you have to do the test. Then we have to find F3. F3 equal to rating factor related to variation of depth of laying. You can see in the table. Rating factor related to variation of depth of laying for 3.3 kV to 11 kV cables. Our depth of laying is 105. Then rating factor is 0.99. So next rating factor is F4. F4 is the cable laid directly in the ground. Then the rating factor for touching. I am assuming I am laying only one cable. So there won't be any factor for touching. This rating factor is for multi cables going together or multi cables in tire formation like that. So I am considering F4 also 1. So F2 equal to 1, F3. The rating factor related to depth of laying equal to 0.99, F4 equal to 1. Then overall the rating factor F equal to F1 into F2 into F3 into F4. That value will be 0.99. Then we have to find the cable current carrying capacity based on the load. That will be load current divided by correction factor. 65.69 divided by 0.99. That will be 66.35. So we know the current carrying capacity of 240 square mm cable is 315 ampere, which is very greater than load current divided by correction factor, that is 66.35. In that scenario, our selection is ideal. So we need minimum 3-core 240 square mm aluminium 11 kV unearthed cable. In this scenario, load current divided by correction factor equal to 66.35. If the value is more than 315 ampere, our cable selection is wrong. Then we have to select higher size cable based on this. In this scenario, the value is 66.35, which is very less than 315 ampere. That's the reason our cable selection is good. If you go back to the cable catalog, from that you can see short circuit current rating for 1 second duration for 240 square mm cable is 22.56. The maximum short circuit distance capacity of the cable is 22.56. What is system short circuit capacity? System short circuit capacity we found as 18.37. This 22.56, that is short circuit current rating capacity of cable, is greater than system short circuit current, that is 18.37. So in this scenario also, our cable selection 3-core 240 square mm aluminium 11 kV unearthed cable is valid. The next step is we have to find the voltage drop. We went to the detailed voltage drop calculation in our LV cable sizing video. We learned how to do it in manual as well as with the help of Excel sheet. I am using same Excel sheet here. Please watch LV cable sizing video, then you will get more understanding about the voltage drop calculation. So in that Excel sheet, have to enter line voltage. Line voltage is 11 kV. Load we have to enter. Length of the cable. What is the length of the 11 kV cable? I am assuming one length is 1000 meter or 1 kilometer. Number of run is 1. Then resistance and reactance. Where will we get this resistance and reactance? Either you will get it from the standards or you will get it from the cable catalog. If you look at the cable catalog, you can see for the 240 square mm for aluminium conductor, resistance is 0.162. Reactance is 0.102. Just enter the values in this column. Resistance 0.162. Reactance 0.102. Power factor I am considering as 0.8. This will be more than 0.8 for sure. For the transmission lines or for the distribution network, this will be around 0.95 to 97. But I am considering 0.8 only for the calculation purpose. So sin phi will come automatically. Just we have to enter the load 1000 kilowatt. Then we will get the voltage drop. Voltage drop is 21.71 volts or 0.20%, which is within the allowable limit. So we can go ahead with our cable size. Let's look at one more problem. Tower A is a project in India which has a maximum demand of 5 MVA and it is fed through a dedicated 33 kV feeder from substation with fault level of 1400 MVA. Find the incoming cable size of the transformer. This is our scenario. we have a project with 5 MVA demand and the project is fed through a dedicated 33 kV line. Let's solve this problem. Our S fault MVA equal to 1400 MVA, line voltage equal to 33 kV, then short circuit current ISC equal to fault level divided by root 3 divided by line voltage. If we substitute these values in the equation, fault MVA equal to 1400 into 1000 divided by root 3 1.732 into line voltage equal to 33 kV. The answer will be 24494 ampere. That is 24.49 kiloampere. So short circuit current is 24.49 kiloampere. What is the equation for cable size? If the conductor is copper, the equation is cable size equal to short circuit current into root T divided by 0.143. ISH or ISC short circuit current equal to 24.49 kiloampere. For the aluminium conductor, the equation will be cable size equal to ISH or ISC into root T divided by 0.094. I am using aluminium cables only. So I am substituting this value in the aluminium cable equation. Here T we will consider as 1 second. The cable size equal to 24.49 into root T divided by 0.094. The answer will be 260.5. So we don't have a cable with 260.5 square mm. So we will go for the next higher size. Next higher size is 300 square mm. So our cable spec is 3 core 300 square mm aluminium 33 kV unearthed cable. The minimum cable size required is 3 core 300 square mm aluminium 33 kV unearthed cable. Is this cable size final? No, it is not final. We have to do 3 more steps. Step 2 is cross check the cable size with load and correction factor. Step 3 is cross check the short circuit rating of the cable. Step 4 is cross check the voltage drop of the cable. I have demonstrated this in earlier example. You can do it as an assignment. That's it guys. I think you got a fair idea about high voltage or high tension cables and its calculations. We'll see you in the next video. Bye bye.